Hello, everybody. It is October 16th at 4 p.m., and I'm going to go ahead and get started with this session. So we are on the second week of a 2-week experiment where we are analyzing motion of objects that we take the videos of. So the point of this assignment is to show you, the real world is a little messy. Yes, we have all of these physical tools in order to help us, approximate motion in the real world, but because, the motion around us isn't going to be perfect, oftentimes these equations don't fit exactly right. But that being said, they do a very, very good job of approximating what it is we expect to see. Now, up until this point, the motion that we've seen, the dry ice puck or the objects that are being thrown up into the air, they've all been really good at minimizing the sort of outside errors that exist in the real world. But when we go and take motion videos of things in the real world and we want to analyze that motion, well, suddenly there might be friction involved, slowing objects down, or maybe motion isn't quite so smooth. If you look at the video from last week, I put up a video of my dog Princess running across the yard. And in that video, you can see that the motion isn't exactly perfect, constant motion. That's because, depending on what part of her stride she's in, maybe she's going a little faster, slower. But overall, the motion follows a pretty good path. Um, uh, some of the videos that you guys post and that you guys are working on. And I see really good examples of motion. I see toy cars rolling across a level surface and getting pretty good constant motion from that, or stuffed animals being thrown up into the air, getting good videos from that. I saw a student, she posted in her exercise a video rolling a can, and rolling a can is a really good option here for constant motion, accelerating motion if you roll the can down the ramp. Um, but what's interesting is that you can see on her constant motion, while like part of the motion does look very constant, it does slow down. The can comes to a stop, and there is some acceleration there because of friction. And again, this is to be expected because in the real world, we see these outside effects. Nothing is as perfect as it is in the lab. So keep in mind as you guys make these videos that your work isn't going to be, as clean maybe as it was in the uh, previous couple of weeks. I want to address a couple of questions that I saw pop up. A couple of students were struggling figuring out how to find out the size of their video file. And I'm going to go ahead and show you right now how to find the size of a video file. Um, I'm going to first show you on a Windows computer because that's what I'm working on. So I can show you on a Windows computer how to find it. And then we will take a look at how to find it on a Apple computer, but that I can only show you like where to find the information of. I don't have an Apple computer to work off of. So looking at the screen, I have, among some other course files, I have this parachute monkey video, and it's not as exciting as it probably sounds. It's not as exciting of a video as a monkey parachuting out of a plane. It's a classic physics example. Anyway, the parachute monkey, if I wanted to see this video file, if I wanted to figure out what its frames per second is, its frame rate, I would first go to properties, and in properties, it will open up this view right here. And if we go to details, in details, it has the frame rate right here. So this one is 32.81 frames per second. It's kind of an odd frame rate, but that's just what the camera recorded it in. Now on your phone, as you record these videos, chances are you can select what frame rate you want to use. Certain phones, especially newer phones, have options to go up to like 60 frames per second. What that means is it's just going to take twice as many images per second as the 30 frame per second. not super important. And here you don't really need 60 frames per second. So if you wanted to limit your video's size, right? Every video has some sort of a size related to how much information is stored on that video. You can use 30 frame per second. You don't have to use the maximum frame rate. It's just not necessary in this lab. Also, on that note, you don't have to use the maximum quality, right? I know phones film in like 4 or some phones even get 8K, I think. Don't quote me on that. But some phones record up into 4K, and you don't really need that sort of resolution either. You can use a smaller resolution. This one video, I think it's like 480p or something. So you don't need a super high frame rate and you don't need a super high resolution for your videos. So that's how you would see it in Windows, right? That's how you get the frame rate. But in Apple, a little bit different. I'm gonna have to edit that out. In Apple, a little bit different. In Apple, the way you would find it is you would have to first go to the QuickTime Player app. It should be on all MacBooks or all Mac uh, computers. And you would open the file that you're looking at. And when it's open, you go up into the window folder and you go inspector and then press Command I, and it will open up some sort of a similar type window as to what we saw on the Windows computer. And it will have things like your frame rate, or sorry, your resolution is the first thing I wanted to show you. As your resolution, and it also has your frame rate right here, encoded FPS. That is your frame rate. That's frames per second. So on Apple or Windows, you can find out the frame rate of your video utilizing, either the file system in Windows or the QuickTime Player app on your MacBook. Okay, I'm gonna go ahead and stop sharing for just a moment. And while I stop sharing, I'm going to open up the physics activity for the week. Okay. Now we are returning back to the same activity we did last week. We're not moving on to a different activity. This is the same activity for both days of the week. And that's because I'm asking you to do kind of a lot here. I'm asking you to upload 3 of your own videos and to analyze a total of 4 videos, starting with the video of Jessie Diggins as she sprints up a hill. And once we go, we upload a video of constant motion. And I've seen a lot of you have already done this, so that's wonderful. Good job. We are looking for a video of a constant acceleration object and doing something like rolling a can down an incline. Perfect way to get this constant acceleration. And then we go down, and this is the one that I'm going to kind of look at today. So with the free fall acceleration, what we want to do is we want to upload a video of something that is just being thrown into the air. And free fall does encompass anything that is moving up as well as moving down. So what I'm going to go ahead and do is upload a video, and I'm actually going to upload that monkey falling, that parachute monkey video. And I select parachute monkey, and then down here, recorded frame rate. I'm going to leave it. Actually, I wonder if it'll let me select 32. Now, so it doesn't let you select 32. So you're going to want to pick 30 for your recorded frame rate if it's around 30. So round to the nearest value for your frame rate. As I said, some videos come at like 60 frames per second. So uh, keep in mind you want to check on that. So let's go ahead. Let's update our video, and successful. We got our parachute monkey. And we press play and we see our monkey fall. Now, what's interesting here is there's also a projectile coming through. This is a classic physics experiment. And what the idea here is that if you take a launcher and you aim the launcher directly at its target, as the target falls through the air, the projectile arcs into the target. And we can get some connecting, and you see them connect right here. This is, again, a classic physics experiment. Now, for this experiment, I am going to show you a couple of things. First off, we want to calibrate. So to calibrate on this video, there's a meter stick here. So I select either end of the meter stick and I say that is 1 meter. Or I could say it is 100 centimeters. Either is fine. We've typically been using centimeters in this class. I just use it again. Why not? And now what we can do is we can track the motion of our objects. So we open up the ruler and perhaps we want to take a look at our falling object. And should we do that? We could select initial position, take a look at our timer. We can say, okay, well, 0, it's at a height of 200, right? And then we maybe advance forward a couple frames. And later on at 0.4667, we are at a height of 150 centimeters. And we are tracking here time and position. Right, and we'd want to take a few other data points in there, obviously, and that would be perfectly fine. But I want to show you something kind of interesting here. What I'm going to do is I'm going to close out the ruler and I'm going to open up this grid. And on this grid, we have, let me expand it. Yes, I need to rotate it back to where it was. Okay, so on this grid, what we have is basically a two-dimensional measuring system. And what I'm going to do is I'm actually going to track the ball here. And we can see the starting point of the ball. I will put it at 0. So I'll put my little grid here, 0, and I'm going to actually restart the frame counter. So I could say at 0, I am measuring a height of 0. And I am also going to insert a column to the right, and I'm going to measure its horizontal distance it traveled. Variable X, variable Y. I think you guys probably will have seen this in your lecture class. Is two-dimensional motion, but if not, we're going to go through and we're going to track some because I think that this is an interesting idea to look at. So we're going to advance forward. Let's see, advance forward. If we advance forward 1 frame, we see that we have 1, 2, 3, 4, 5. We have 10 ticks before we get to 100. So every line here represents 10 centimeters. So at this point, I would say its horizontal displacement is about 10 centimeters. So this is a time 0.0333. Our horizontal displacement is about 10 centimeters. And our height here, well, I'd say that's probably about 7, right? Not exactly, maybe even 8. We're going to estimate. We're going to do our best to estimate the height. And then we're going to advance forward another frame and we see, okay, well, here we are at probably about, I don't know, we'll say that's about 15 for our height. And about 20 for our distance, and this is at a time 0.0667. And then we advance forward again. And then we see, okay, well, here we are at 30. Our height here, well, that is about maybe, we'll say 22 centimeters, and this is at a time 0.1. And then we advance forward again, and we see, okay, well, now we're at about 40 at 0.133 seconds and a height of we maybe say that's about 29. And then what I do, I might want to insert a row below, and we'll do 3 more measurements. Why not? So we go forward, do another measurement. Now here we are about, I'd say that's about 51 for our vertical distance, or sorry, horizontal distance. Our vertical distance is 10, 20, 30. We'll call that 32, 32, 33. And just estimating, right? It's not a perfect measurement by any means. Go forward. Okay, now we're at 62 centimeters on the horizontal, and then vertical, we're at 10, 20, just shy of 40, so we'll call that 39, and that's at 0.2 seconds. And then we go forward one more frame. Here we are at horizontal distance 72-ish. We call that maybe 41, 42, we'll say 42 centimeters, and this is at 0.233. All right. Now I go through this because when we take a look at the graphs that we can create here, we want time to be on the horizontal. And on the vertical, we actually have 2 distances that we are measuring. We're measuring vertical distance and horizontal distance. And if we look at our horizontal distance, well, we have a straight line. We insert a curve fit. Let's insert a linear curve fit. And we have 310 centimeters per second. That's our horizontal speed. This is like our land speed, we sometimes call it. This is how fast we're moving horizontally, and it ends up being a really nice linear line. So we have straight line motion, we have constant velocity when we look at the horizontal motion of a projectile, an object moving in 2 dimensions. But when we look at the vertical distance, the height that we measure over time, well, with the height, we actually have something that fits more of a quadratic. We see that the lines match up pretty well with a quadratic here. So our ball here measures a really nice accelerating motion. And in fact, if we look at the curve fit, the A term 310 centimeters per second squared, well, that should roughly equate to the acceleration due to gravity. Now, this isn't a great experiment. We weren't very accurate with our measurements as far as this particular video goes, but we have a really nice example here of accelerating motion, and in fact, the ball's free fall motion when we talk about its vertical displacement. So I just wanted to show you guys this because, well, there's a couple reasons why I wanted to show you this. This video gives you a really good example of some of the tools we have at our disposal on these video analysis software. We have this nice grid here, which can tell us both the vertical and horizontal positions. But I also wanted to show you how we can utilize these graphs because we have time, height, distance. We can add columns, we can add rows, we can add in the data that we want to take. And really the important reason why we take a look at this, adding a column, because I know many of us preferred the method of measuring our acceleration by first finding the velocities. So here's what I'm going to do. I'm going to graph out velocity, centimeter per second, and we're going to base this velocity off the vertical position based on the height. I am going to need to delete all of this data. Uh, there we go. Now it's letting. There we go. So I know a lot of us liked looking at that velocity versus time curve and finding out the acceleration based off of that. And we can do that here. So what I'm going to do, curve fit, I'm going to look at the linear fit to this, and we are going to specifically just select a few data points at a time. So when we select the first 3, we get a velocity here of 225. So for the first three, we would say 225 is our velocity, and we don't actually have the value there. So I'm going to delete that 0 if it allows me, and it doesn't seem to. You know what? We'll shift things up. We'll put 225 there. Okay, and then we look at the next three data points, and we get 210. So we analyze the next three data points here and get 210 centimeters per second. Then when we base the curve off of the next three, we see, okay, well, that one came off as 210 as well. And this is because there was inconsistencies in our measurements. Again, these videos are no longer the nice, perfect videos we've been dealing with. The next 365. And then the next three data points, we have 150. What's nice here is that we are seeing a generally decreasing velocity, indicating that we are in fact accelerating. Here we have 135 centimeters per second. And now we have measurements of our velocity. And when we look at our velocity versus time, well, hopefully what we'll see is that data point is really suspect. I want to go back and double check something actually. Base it off of those three. We got 210. Those three, we also got 210. Okay. So I think I just had some poor measuring here, but let's take a look at vertical velocity versus time. And what I'm going to do is base it on all of our data points. And when we do, we see acceleration 578, about 600 centimeters per second squared. Now, that is not the acceleration due to gravity, right? That's 980. This is quite a fair bit off. And you might ask, well, why is it a fair bit off? And it is because there are outside effects going on here, right? You have air resistance, you have all sorts of stuff going on. Again, the motion in this lab is not going to be perfect. Here, the motion is not perfect, but it still is an object that is under the influence of this gravitational force, and we have a way to find its acceleration. And a quick note, negative is good. We got a negative indicating downward acceleration. That's what we would expect here. Okay, so wanted to show you just in this video some really powerful tools we have here in our pivot of the week. I'm going to stick around for a little while longer and answer any questions, but I'm going to end the video here. If you have any questions, just let me know, and I'll be sure to get back to you. Let me close out. All right. And next week we are going to be back having a 1-week lab, and that 1-week lab will be on forces, and it will have a discussion section at the end of it. I know this week did not. That is intentional. That is because this is your work. Next week, you absolutely will have a discussion. If you have any questions, again, don't hesitate to ask, and I will see you all next week.